This is topic 1.3, elemental composition of pure substances, and what we're going to do is we're going to look at the relationship between the chemical formula and the percent composition of molecules. And for the textbook pages, go ahead and look at pages 80 through 90 for this topic. So let's talk about the composition of pure substances. And when I say pure substance, all I mean is that there's a fixed composition. So what does this mean? It basically means that the elements are present, and in the ratio of those elements' atoms is the same for every sample of the compound. So the ratio of the elements present is the same. Let's look at two common examples of everyday life. Sodium chloride, table salt. Sodium chloride's NaCl. It has a ratio of 1 sodium for every 1 chlorine atom. If you don't have a 1-to-1 ratio, you do not have sodium chloride. Another example would be water, H2O. So for every 2 hydrogen atoms, there's 1 oxygen atom. If you do not have this ratio, you do not have water. So this also means that there's a constant mass ratio of elements in every compound. So for every sample of sodium chloride, the mass ratio should be 39.34% sodium to 60.66% chlorine by mass. For water, it should be 11.11% hydrogen and 88.89% oxygen by mass. This is because hydrogen's mass is way smaller than oxygen's mass. And so even though there's double the amount of hydrogen atoms, it's a lot less in mass compared to the oxygen. So for percent composition, let's go ahead and look at an example problem. And with this example problem, we're going to try and figure out the percent composition of sucrose, which is C12H22O11. And what we're going to do is we're going to try and kind of stepwise do these types of problems so you can apply these to anything that you might come across. So step 1, you're going to multiply the number of atoms by the atomic mass to find the mass per element. This is exactly what we did when we were trying to find the molar mass of a molecule. And so what we're going to do is we have carbon, and there are 12 atoms of carbon in sucrose, and we're going to multiply that by the molar mass. So let's go 12.01 is the molar mass. Again, I find that on the periodic table, and I'm going to get 144.12. We do the same thing for hydrogen. So for hydrogen, we have 22 molecules of hydrogen. We're going to multiply that by the molar mass, again, found on the periodic table. I'm going to round it to 1.01. And when we multiply that out, we get 22.22. And the last one for oxygen, we have 11 molecules of oxygen times 16.00 for the molar mass, again, according to the periodic table, and we have 176.00 for that. Now, what we're going to do is the next step, which is going to be to sum the results to find the total formula mass. And so basically, what we're going to do is we're going to add 144.12 plus 22.22 plus 176.00. So let's go ahead and do that and figure out what our total formula mass is. And when we go ahead and add all of those up, we're going to get 342.3 as our formula mass. So now, to find the percentage of each of the elements in the total compound, what we're going to do is we're going to divide the mass of each element by the total mass and then multiply by 100 just to change it into a percent. So what that's going to look like is we're going to take the mass of just the carbon, 144.12, and we're going to divide it by the total mass, which is 342.3, and then we multiply it by 100 to turn it into a percent, and you should get 42.10% carbon. If we do the same thing for all of them, 22.22 divided by our total mass of 342.3, we should get 6.49% hydrogen, and 176.00 divided by 342.3 times 100 equals 51.40% oxygen. Quick way to check to make sure that you got it right is the percentages should all add up to 100 if you've calculated it for each of the atoms that make up the original molecule. All right, so here's an example, and what I want you to do is go ahead and pause it, see if you can set this problem up and go through the steps that we just did on your own before you watch the rest of the video to see how I did this problem. So for the first step, again, you're going to find the mass of the individual atoms that are present. And so for the first one, we have nitrogen. And so we have 2 atoms of nitrogen, and we're going to multiply that by the mass of nitrogen, which is found on the periodic table, to be 14.01. And you get a total mass of nitrogen in this molecule of 28.02. For oxygen, we have 4 atoms of oxygen, and if I again look at the periodic table, I'm going to see that the molar mass is going to be 16.00 for oxygen. I multiply that out and I get 64.00. Next step would be to sum these two up to find the total formula mass. I add those two together and I get 92.02. Now what you do is you take your mass of the individual nitrogen in the compound, so we got 28.02. I'm going to divide it by 92.02. Multiply it by 100 to get a percent, and I'm left with 30.45% nitrogen. And so then what you can do is you can divide the oxygen out, or you can just subtract 100 minus 30.45 to get the rest. But I'm going to go ahead and divide it out. 64.00 divided by 92.02. Multiply it by 100, and you're going to get 69.55% oxygen. Again, these two should add up to 100% because the molecule is only made up of nitrogen and oxygen. So now let's truly understand what percent composition is. So can 2 different substances have the same percent composition by mass? And the answer to that is yes, they can. So now let's talk about why, so we can truly understand what this percent composition is. Because again, you might not have to calculate percent composition on the AP exam, but you will probably have to understand what percent composition is, or something conceptually that has to deal with percent composition if you're not asked to do the calculations. So what does this mean? Well, if we look at 2 molecules, we have the chemical formula NO2 and N2O4, okay? 2 different molecules, but they both have the same ratio of nitrogen to oxygen, and that ratio is 1 to 2. You can see that in the highlighted boxes. And so if they have the same ratio, then they're going to have the same percent composition, because for every 1 nitrogen molecule, one nitrogen atom, there's going to be 2 oxygen atoms. And so the percent composition remains the same, even though that chemical formula is different and these are 2 different molecules. And that percent composition ends up being 30.45% nitrogen and 69.55% oxygen for both of them. So yes, 2 different substances can have the same percent composition by mass if they have the same base ratio. So again, okay, make sure you understand this. If different compounds have the same smallest whole number ratio of atoms, the composition by mass of those compounds is going to be the same. So now let's talk about the 2 vocabulary words that we've been indirectly talking about. And so the lowest whole number ratio of atoms in each element in a compound is called the empirical formula. So the lowest whole number ratio is the empirical formula. The actual number of atoms of each element in a compound is going to be its chemical or molecular formula. They can use those interchangeably, chemical or molecular. So now let's go ahead and see what that means. So if we have if we compare formaldehyde and glucose, so those are in the green in the table on the bottom, formaldehyde has a molecular formula of CH2O. That's the exact number of atoms that are in a molecule of formaldehyde. Well, if you notice, you can't reduce any of those numbers because there's only one carbon atom and one oxygen atom. You cannot go lower than 1. So in formaldehyde, the molecular formula is the same as the empirical formula, which is the lowest whole number ratio of CH2O. But if you look at glucose, the molecular formula for glucose is C6H12O6. So that means there's 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Now, all of those numbers can be reduced by 6. So if you divide 6 divided by 6, you get 1. 12 divided by 6, you get 2. And 6 divided by 6, you get 1. So the empirical formula is actually going to be CH2O, which is the same as formaldehyde. So you're going to have the same percent composition in glucose and formaldehyde, even though their molecular formulas are different. The same holds true for nitrogen dioxide and dinitrogen tetroxide, which we just looked at in the previous slide. So now let's go ahead and review that concept of empirical formula versus molecular formula. So here I give you 3 molecular formulas and I ask you to find the empirical formulas of each. So pause the video and see if you can go ahead and do that, and then push play and see if you got it right. So let's go ahead and look at this first one. So we got H2O2. And so basically what you're doing is you're finding how to reduce this. And both of these can be reduced by 2. And so the empirical formula for this is just going to be HO. For every 1 hydrogen, there's going to be 1 oxygen. For Na2SO4. Well, if you look, we only have 1 sulfur atom. So 1 can't be reduced any further. So this is actually going to stay the same as Na2SO4. So for every 2 sodium atoms, we have 1 sulfur atom and 4 oxygen atoms. That's as low as we can go because of that 1 sulfur atom. And finally, we have C2H4O2. And so if we look at that, they can all be divided by 2. So that's how we're going to reduce it. And so we have 2 divided by 2 gives us 1 carbon. 4 divided by 2 gives us 2 hydrogens. And 2 divided by 2 gives us 1 oxygen. So the empirical formula of C2H4O2 is going to be CH2O, which just means the ratio is 1 carbon atom for every 2 hydrogen atoms for every 1 oxygen atom. So now let's go ahead and look at how this could potentially show up on an AP exam. Now AP exams love lab data. They love to give you data and ask you what does this data mean, and you have to try and analyze what's going on. So here, a compound was analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What's the empirical formula of the compound? Now, this seems like a really complicated problem, but if you break it down into 3 easy steps, it's actually pretty simple. It's just a bunch of multiplying and dividing the right numbers to get your answer. And so converting mass to moles is exactly what we did in section 1.1. So again, this is kind of cycling back and just adding on information to what we've already learned. So let's go ahead and figure out how to convert the masses to moles that were given in the problem. So the first thing you do is you start with what you know. And so let's start with calcium first because it's listed first. And what we know is that we have 13.5 grams of calcium. And so then we do our bracket. Okay, grams is on the top, so we're going to have grams on the bottom. And if you look at your periodic table, okay, the molar mass of calcium is 40.1 grams for every 1 mole. Grams cancels out, and we're left with moles. So if you divide that, because we have a number on the top and a number on the bottom, that horizontal line, again, remember that's just a division sign, gives us 0.337 moles of calcium. Again, I'm going to make sure that I use calcium in my units so that I remember what I'm talking about. The next thing that we're given is 10.8 grams of oxygen. I'm going to do it the same way. I look at the periodic table and I know that oxygen is 16.0 grams per 1 mole. And so I cancel out my grams. I divide it out and I get 0.675 moles of oxygen. Again, I'm not doing this math in my head. I'm using a calculator. You can use your calculator to do this math. The last thing that we're given is 0.675 grams of hydrogen. And if I look at my periodic table, I'm going to say that hydrogen is molar mass of 1.01 grams for 1 mole of hydrogen. And if I divide that out, I get 0.668 moles of hydrogen. Okay, I'm done with step 1 because I converted all of my masses to moles. Step 2 says divide all by the lowest number of moles. So we have to figure out in step 1 what is our lowest number. And our lowest number is actually this calcium right here. 0.337 is the smallest number. So what we do here is we're just going to go 0.337 divided by 0.337. And that's going to give us 1 because we're dividing by the same number. So that's 1 mole of calcium. Then we go 0.675 divided by 0.337, and we get approximately 2 moles of oxygen. And then 0.668 divided by 0.337, and we get, again, approximately 2 moles of hydrogen. So now that basically gave us the ratio. So use the mole ratio to write the chemical formula. And so what I'm going to do is I'm going to use these numbers, 1, 2, and 2, to write my chemical formula. So I have Ca, and there's 1 of them. Then I have O2, because there's 2 of them. And then I have H2, which there's 2 of them. Now, technically speaking, this is right, but if you were to recognize how we write this differently in chemistry, and again, this isn't going to be like now, but later on in the course, you might recognize this as calcium hydroxide, and we're going to write that as CaOH2. And again, either one of these is correct. They're not going to mark you off points, but technically speaking, you would write it like the bottom one. Right there. So they could throw you a curveball and they could give you percents. So in this problem, we have to do one extra step, but it actually is not as hard as it's going to look originally. So a compound is determined to be 43.6% P and the remainder oxygen. What's the empirical formula of the compound? Well, first off, if we have 43.6% phosphorus and the remainder oxygen, we do know how much oxygen is left because we would just subtract that from 100. But what we're going to do is we're going to convert percents as masses to moles. And so instead of saying 43.6%, we're just going to pretend that we have 100 grams of this substance because the amount of grams doesn't matter because they're going to be in fixed ratios. So we're just going to pretend we have 100 grams of this and use the percents as grams. So the problem gives us 43.6 grams phosphorus. If we look at the periodic table, we know that this is going to be 30.97 grams for every 1 mole, and that's going to give us 1.408 moles of P. Again, I'm just going to take this number and subtract it from 100, and that's going to give me the amount of oxygen. And if I do that, I get 56.4 grams of oxygen. And if I look at my periodic table, the molar mass of oxygen is 16.00 grams of oxygen. Those cancel out for every 1 mole. And if I divide those out, I get 3.525 moles of oxygen. The next step is the same. I'm going to identify the lower number of moles, which is 1.408, and I'm going to divide all by that lowest number. So I have 1.408 divided by 1.408 equals 1 mole phosphorus, and I have 3.525 divided by 1.408, and I get approximately 2.5 moles of oxygen. Now, let me ask you this. Can you have 0.5 of an atom? And the answer should be no. So if you ever end up with 0.5 of something when you're doing this, basically all you have to do is multiply top and bottom by 2. So you multiply both of these by 2, and you're left with 2, and you're left with 5. And so those are the mole ratios that you're going to use. So that's what that step 3 is. Okay, step 3 is just multiplying them so that you have whole numbers here. And then step 4, we're going to use those numbers to write the empirical formula. So we have P2O5, and we are done. So go ahead and try this problem on your own. Again, it's the same type of problem that we just did. You're given percents, and you're asked to find the empirical formula of that compound. So go ahead, work through the steps, and then go ahead and press play, see if you got it right. So step 1 would be to convert those percents to masses, and again, they're just going to be the same. We're going to assume that we have 100 grams of the substance, and we are going to convert the masses to moles. So let's start with the potassium since it's listed first. We have 28.7 grams of potassium. Look on the periodic table, and you have 39.10 grams for every 1 mole, and that leaves us with 0.734 moles of potassium. Next, we're given 1.5 grams of hydrogen. If we look on the periodic table, it's going to be 1.008. Again, you can put 1.01, just whatever your periodic table says. As long as it's close, it's not going to make a difference because the significant figures aren't going to change. And you're going to get 1.49 moles of hydrogen. We're given 22.8 grams phosphorus. Periodic table says it's 30.97 grams for every 1 mole. And we divide that out, we get 0.736 moles. And the last one they give us is 47.0 grams of oxygen. 1 mole of oxygen for every 16.0 grams. We divide that out, we get 2.94 moles of oxygen. We identify the smallest amount of moles, which is going to be our potassium that we did first. And we divide all of our numbers by that 0.734 moles. And once you do that, you have your mole ratio, and so you can use that to write your empirical formula. So I have KH2PO4, and all of these numbers are coming directly from my mole ratio. So now, how are you going to see the empirical formula on the AP exam? You could have it 3 different ways. The first way would be a straightforward mass or percent composition data to empirical formula. This is what we've been doing. That's a pretty simple problem. You might see one, but it's probably not going to look like this on the AP exam. But there have been some in the past. The second way that you can see it is a combustion analysis, and this one's a little bit more interesting, and we're going to look at an example in the last slide of this presentation. But basically, we're burning a sample in oxygen, so a combustion analysis means that we have a carbon, hydrogen, we have a hydrocarbon, so it's a mixture of carbon and hydrogen, and we have oxygen, gas, so O2, in the reactant side, and we are left with carbon dioxide and water on the product side, and we're given what the products are yielding, and we're trying to figure out the original ratio of carbon to hydrogen. So that one's a little bit more interesting. You could see that one. And then finally, we have a hydrate analysis, which is heating hydrated ionic solid and analyzing the mass change to determine the mole ratio of water to anhydrous solid. We're actually going to do this lab because they like this question because it has a lab that goes with it that we're supposed to do in AP. So you could see this one as an FRQ. Hopefully you do, because I think it's an easier FRQ style question. For part of the FRQ, they also like to throw in mixtures of other units. But this would be the third type, and again, they like this third type because they can tie it into the lab portion of the class. So let's go ahead and look at each of these examples and see how you would kind of see these on the AP exam. So this is the first type of problem where they're giving you data and they're asking you what the empirical formula is. It's a multiple choice problem, so they have kind of nice numbers. You don't necessarily have to use your calculator on it. Before, they wouldn't let you use calculators on multiple choice exams, but I think they changed it. So you would be able to use your calculator, but it might be faster just to do it in your head if you can. So a 23-gram sample of a compound contains 12 grams of carbon, 3 grams of hydrogen, and 8 grams of oxygen. Which of the following is the empirical formula of the compound? So again, we are going to go with what we know. We know that we have 12 grams of carbon, and we're going to want to convert that into moles. And so the way that I'm going to do that is I'm going to divide it by 12 grams of carbon for every 1 mole, and we get 1 mole of carbon. We have 3 grams of hydrogen. For every 1 gram of hydrogen, I'm just estimating here, for every 1 mole, and we get 3 moles of hydrogen. And we have 8 grams of oxygen. And I know the oxygen is 16 grams for every 1 mole, and so that leaves us with 0.5 moles of oxygen. Next step would be to divide by the smallest amount, which is this 0.5. So if I divide this by 0.5, I get 2 moles carbon. If I divide this by 0.5, I get 6, and if I divide this by 0.5, I get 1. And so my empirical formula should be C2H6O, and if I look at my answer choices, answer choice B is C2H6O. All right, so here is our first FRQ for this style. This is going to be the hydrate example that I talked about, so 3 in the example types of problems. And so here we have a student that's assigned a task of determining the moles of water in 1 mole of MgCl2 in H2O. So we don't know how many moles of water there are in the sample. The student collects the data as shown below. And again, you guys are going to do this lab, so it's going to be familiar to you. Again, I hope that they give you this type of style of question on the AP exam, because once doing it, I think you'll understand this a lot better. But we have the mass of the empty container, the initial mass of the sample. We're going to go through all of these and how we're going to use them. But I really want you to think through what you're given when we're doing this. So if we have the mass of the empty container and the initial mass of the sample and the container, we can find the initial mass of the sample. If we have the initial mass of the sample and container and the mass of the sample and the container after the third heating, we can find the mass of the sample after we heated everything and boiled off all of the water. And so you have to kind of understand how to use these numbers and not just memorize kind of, oh, this is what you plug in here. So really understand what the numbers mean and what you can find from them. So explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. Again, they like these problems because they're actually based in the lab. So what are we doing? We're heating a sample, and it's asking us, how do we know that it was heated enough? Well, if we look at the mass of the sample in the container after the second heating and after the third heating, the mass doesn't change a whole lot, and it actually goes up 1, which we can kind of assume that that's the error of the balance. And so we know it heated enough because it didn't change mass anymore. And so we know that we heated all of the water out of the sample. And so to write that in the AP exam, again, you have to be very clear in what you're stating. So this would be an example. The student can conclude that the hydrate was heated a sufficient number of times because the mass of the sample in the container does not change significantly between the second and third heatings, indicating that all of the water has been removed. So that that last part is really important, showing that you understand what you're saying. So now let's go ahead and go to part B. So we have to use the data in part B. So the first thing that we're going to do is we're going to calculate the total number of moles of water lost when the sample is heated. So let's focus on that. How are we going to do that? Well, how do we get to moles of water lost? Well, to get to moles, we have to find the mass of the water lost. And so how are we going to find the mass of the water lost? Well, basically, what we're going to have to do is we're going to have to figure out. So we're going to use the initial mass of the sample in the container, and we're going to use the final mass of the sample after the third heating, and if we subtract those two numbers, we should get what was lost, and we know what was lost was the mass of the water. So if we subtract those two, okay, so we got 25.825 grams minus 23.977 grams, we are left with 1.848 grams of H2O. So that's the mass of the water that was lost, but that's not what it's asking us. It's asking us to calculate the total number of moles lost. So now to get moles, we have to find the molar mass. So the molar mass of water So hydrogen is going to be 1.01, and there's 2 of them, so I'm going to multiply that by 2, and I'm going to add oxygen, which is 16, and so that's going to give us a molar mass of 18.02 grams per mole. Again, I got those numbers from the periodic table. And so now I'm going to draw my brackets. We have 1.8 we have 1.848 grams of water, and I'm going to divide that by 18.02 grams for every 1 mole. Okay, grams cancel out, and I am left with 0.1026 moles of water. Now I want to determine the formula of the hydrated compound. So now what we have to do is we have to figure out how much of the MgCl2 that we have after we boiled all the water off. So basically what we're going to do that is we are going to take the final sample here, because that should not have any water in it. So we're going to take this sample here, and we're going to subtract the container because we don't want the mass of the container in there. So this was part I, this is going to be part II. So we're going to take 23.977 grams minus 22.347 grams, and that's going to give us 1.630 grams of MgCl2. So again, I'm going to explain that one more time onto why I picked those two numbers. So the mass of the sample in the container after the third heating should just have the MgCl2. It shouldn't have any water in it. And if we want just what's in that container, all we have to do is subtract the container. Well, we have the mass of the empty container that we found first, and so we just subtract that number from it, and that should just give us the mass of the anhydrous MgCl2, or the MgCl2 with no water in it. Okay, then what we do is we do the same thing when we were trying to find the number of moles of H2O, is we have to find the molar mass of MgCl2. So molar mass of MgCl2, and again, we're going to look at the periodic table, and we're going to add up 1 atom of Mg and 2 atoms of Cl2, and if we do that, we're going to find the molar mass as 95.21 grams per mole. And so we're going to use that to convert this 1.630 grams to moles. So we have 1.630 grams of MgCl2 and the molar mass is 95.21 grams for every 1 mole. And if we divide that out, we should get 0.01722 moles of MgCl2. So now basically what we have to do is we're going to do the ratio, and so we're going to divide by the smallest number of moles, and the smallest number of moles is this MgCl2, so we're going to divide this top by 0.01722 and divide this number by 0.01722, and so we're left with 1 and approximately 6. It's going to be like 5.992 or something like that. That's about 6. So close enough for our purposes. So the equation here that we were trying to find is for every 1 of these MgCl2 molecules, we actually have 6 water molecules. So the way that we would write that would be MgCl2, and then that dot is meaning that it's a hydrate, and we're going to put 6 H2O. All right, so here's another multiple choice problem. And so we have a 3.22 gram sample of an unknown hydrate of sodium sulfate, Na2SO4X H2O, and it's heated. H2O, the molar mass is 18 grams, is driven off. The mass of the anhydrous sodium sulfate, the molar mass of 142, that remains is 1.42 grams. The value of X in the hydrate. So it's basically a multiple choice question asking us exactly what we did in the previous problem, but it doesn't give us a table. It just gives us kind of words, and we have to kind of figure out what's going on here. So the first step would be to determine the moles of water. Well, it gives us the initial mass, and it gives us the mass that remains at the end. So all we're going to have to do is subtract those two. So when we do that, we're going to take 3.22 minus 1.42, and we're going to be given, or we're going to be left with 1.80 grams of H2O. And it gives us the molar mass, and it wants us to use 18. So if we have 1.8 grams of H2O, and we want to calculate how many moles of water that is, we're dividing it by 18 grams of H2O for every 1 mole. And so we're left with 0.1 moles of water. The next step would be to figure out what number of moles of sodium sulfate we have. And so we are left with 1.42 grams, and so that's going to be our sodium sulfate. And again, you didn't have to know this was sodium sulfate actually for this problem, because it gives you the molar mass already, so it's not something you have to calculate. And so we have 142 grams for every 1 mole. And if we divide this out, we get 0.01 moles of sodium sulfate, Na2SO4. Again, we will learn how to calculate this Na2SO4 later on. You don't have to know that that's sodium sulfate yet, though. And so now what we do is we divide both numbers by the lowest mole ratio. And so this should be 10, and this is going to be 1. So we should have our answer as 10, which is D. So here's the combustion example I was talking about earlier on. So we're told that we have a sample of a compound containing only carbon and hydrogen atoms, and it's completely combusted, producing 5.65 grams of carbon dioxide and 3.47 grams of water. The question is, what is the empirical formula of the compound? So why don't you pause and try and work through that. Now, let's make sure that we understand what is going on. So we have a mystery compound that contains only carbon and hydrogen. So we have a number of carbons, and I'll call that X. and we have some number of hydrogens, which I'll call Y. And then when placed in the presence of molecular oxygen, it combusts and produces carbon dioxide and water. So when we put this with oxygen, it's going to combust and form carbon dioxide and water. What I've just described is a chemical reaction, though I haven't balanced it yet, and balancing it with X's and Y's isn't the point of this example. So we're not going to worry about that for right now. The key information is that we're given the mass of carbon dioxide and the mass of water produced. And from these values, we can actually calculate how many moles of carbon dioxide and how many moles of water are formed. And then from that, we can determine how many moles of carbon dioxide and hydrogen were present in the original compound. So we can work backwards and actually figure out what the original compound was. So by looking at these ratios of elements, we're going to now determine the empirical formula for the compound. So first off, I'm going to write some molar masses so that I don't have to look at the periodic table, so that we have them handy. So the first molar mass we're going to need is going to be hydrogen, and let's say that the molar mass is 1.008, again from the periodic table. Carbon, we're going to use 12.01. Oxygen, we're going to use 16.00. And then we actually are going to need the molar masses for carbon dioxide and water too. So CO2, again, 1 carbon, 2 oxygens is going to come out to 44.01. And H2O is going to come out to 18.016. If I didn't round, if I did round, you could have rounded it to 18.02, which is close enough. So now what we're going to do is we're going to have to figure out the amount of moles in each of these. So let's go ahead and try and find moles of carbon first. So moles of carbon. So we're given that and the only place that we find carbon in our two products is going to be CO2. So we're going to take the mass of the CO2. So we have 5.65 grams of CO2. And I have the molar mass of CO2 already calculated as 44.01 grams of CO2 for every 1 mole of CO2. And when we divide that out, we should get 0.128 moles of CO2. Now, that's not really what I want, because the question is asking us of the empirical formula of the compound, and in the compound we're only worried about carbon and hydrogen, not carbon dioxide. But the carbon in the carbon dioxide could only come from one place, and so that's what we're going to use. So we know that there's only 1 carbon in this molecule. So we know that for every 0.128 moles of carbon dioxide, we actually have the same amount of moles of just carbon. So now we're left with 0.128 moles of carbon, which is what we wanted. So now let's look at the moles of hydrogen. So now the only place in the products that have hydrogen is going to be this water molecule. And so we're going to start with this 3.47 grams of water. I have the molar mass of hydrogen, or not hydrogen, water, as 18.016 grams for every 1 mole. And when we divide that out, we should get 0.192 moles of H2O. So now this one is a little bit interesting, because if we have 0.192 moles of H2O, how many moles of just hydrogen do we have? Well, we have 2 hydrogens in the molecule, so we actually have to multiply this number by 2 to get moles of hydrogen, because we have 2 moles of hydrogen here. And so that turns out to be 0.385 moles of hydrogen. So now all we have to do is we find the ratio, and so we divide this number divided by 0.128 because it's the smallest. We divide this number by 0.128 and we're left with 1 carbon for every 3 hydrogens, and so the empirical formula of the compound should be CH3.